Hello, good day. I'm here to present our research paper, a multi-stage transfer learning approach for acute lymphoblastic leukemia classification. I'm Renato Maaliw III. In behalf of my co-authors, I'm presenting this paper. So leukemia is a life-threatening cancer. It is caused by the growth of abnormal blood cells, and it leads to immune systems degradations. So World Health Organization in 2020 shows that there are 400 plus cases out of the 18.1 million cancer instances worldwide, or it has a share of 2.6%. So understanding the exact type of its nature at an early stage enables the physicians to accurately anticipate a patient's prognosis and treatment. Acute lymphoblastic leukemia, or ALL, is a fatal blood cancer brought by immature lymphocytes. So it has been classified by the French American system, L1, L2, and L3, depending on the size of the blast, as you can see in the figure. For its diagnosis, hematologists perform microscopic blood smear examinations. So this is the sample of the microscopic blood smear. This process is manual, complex, costly, and time-consuming to differentiate between the characteristics of normal versus immature leukemic cells. But unfortunately, the errors in medical image interpretation are not negligible, as it heavily relies on the pathologist's expertise and experience. So experts recommend using accurate yet economical, intelligent, automated system using AI against the labor-intensive manual diagnostics. Based on literature, there are many who attempted to identify leukemia by using feature extraction and segmentation, but they have significant drawbacks due to adaptability and scalability. So for our research, we aim to advance the medical image analysis by developing a comprehensive pipeline and procedures through extracting structural information efficiently. So by considering the long distance dependency of microscopic images, so in a 4-level classification anchored on a multi-stage deep learning network approach, we can produce an accurate classification to benefit medical practitioners to evaluate acute lymphoblastic leukemia. So for the methodology, so we have collected 100 ALL-DB1 dataset. It is 24-bit, so 39,000 labeled lymphocyte for classification. Another dataset is a cellular level with 240 instances for detection, also 24-bit and 257 by 257 pixels. So we will use it for segmentation. So for the data processing, we use the monochrome filter. As you can see in the figure, it is very efficient on discarding unnecessary information to discriminate the lymphoblast. So we remove some blood components, as you can see, by using the monochrome filter. For image segmentation, we utilize a modified residual unit for the white blood cell segmentation. So our modified residual unit has the encoder and decoder mechanism. So as you can see in the figures, it separates the lymphoblast completely and totally isolate it, which is very helpful in terms of a deep learning algorithm if you are only concerned on the lymphoblast. So because we have a small data set, so we enlarge the data set using a synthetic method. We flip, rotate, shift, or scale. So by doing this, we produce additional 1,360 instances. So for a total of 1,700, which is sure well-balanced data set. So for our pipeline, so we acquired images of blood cell images. Then we filter in monochromatic mode. Then we segment using residual unit and we augment the data. So the first stage of our approach is to use natural images based on the ImageNet and fine-tune it with using different neural network architectures. The second stage is to use the ALLDB2 dataset or the cellular level dataset. And the third stage is to train based on the old DB1 dataset. So the classification will be the detection, which is normal or the existence of leukemia, while the classification is a 4 category from normal, L2, L2, L1, L2, L3. This is based upon the French and American British classification of leukemia. So for the block diagram of our deep CNN networks, so we use several configuration like the input layer, batch normalization, and the max pooling and the global average pooling with a softmax activation function. So here are the block diagram for each convolution per stages. So more on this if you read the paper. So for hyperparameter optimization, we use sequential based optimization. So based on our hyperparameter optimization, these are the mean fine-tune configuration from epoch to shuffling mode to the optimizers and batch sizes. So for the performance metrics, so we use the accuracy, precision recall, and F1 score. So for the result, so in terms of convergence loss plot, so it is understandable that if you use a multi-stage transfer learning approach, it will take time to reach equilibrium compared to a single pace transfer learning. So, but we gain in significant error loss with a fine-tune parameter. As you can see in the graph, we have the 3-stage transfer learning with fine-tune. So although it takes time to train, but it is more accurate than other configurations. For the leukemia detection, so the Inception ResNet V2 performs well with 99.6% accuracy. Although the Inception V3 rank last, it is also have a respectable accuracy of 97.80%. In terms of classification, so the Inception ResNet provides a 94.67 accuracy, while the Inception V3 rank last with 87.83% for the normal, L2, L2, and L3 classification. So for in terms of classification quality, so same result. So based on the graph, so it exceeds the randomness. If you can see, most are beyond the random guessing line, the diagonal broken line. And it has a AUC scores that signifies it is accurate. In terms of confusion matrices, so most errors originated from the L1 normal combination, so L2 L3 with 6.18% and L2 L1 L2 with 5.77%. So for the Inception ResNet training validation loss and accuracy, so we seen the conversions from 65 to 100 epoch, and we see stabilization at 160th. That's why the maximum epoch we provide is 160. And also at 154th epoch, it achieves highest accuracy of 97.78 and 97.89 respectively. So in terms of the classical versus the multi-stage transfer learning approach, so we tried 10 times for specific random images. So based on the t-test, it has a significant difference between the two sets with a p-value of 0.001. So we have the default value of 0.05. So the accuracy when using the multi-stage transfer learning approach that we proposed, it has an increase of 4.71% accuracy. So our experiment verified that multiple stages of transfer learning using multiple stacks of pre-trained CNNs elevated the performance of leukemia identification. The progression of training using natural images benefited the knowledge abstraction of the lymphoblast characteristics. So the result indicates that the Inception ResNet B2 surpasses other models with the 99.6% accuracy for detection and 94.67% accuracy for classification. It also downsizes error rates by a mean of 1.65% and 6.05%. It is a noteworthy gain in terms of image processing. So confirmatory trial tests revealed that our multi-stage transfer learning approach has a 5% significant positive difference between the classical single-stage transfer learning. So this work remarked that complex neural network architecture did not necessarily usher in high metric scores because each neural network architecture has its own advantage or disadvantages based on the medical image domains. So of course, we encountered noisy blood scan, which has low picture quality, and it causes prediction discrepancy. So we did not consider any solutions for mitigating these issues, such as graphic enhancement and reconstructions. For the conclusions and recommendation, so acute lymphoblastic leukemia is a blood cancer that advances quickly in the absence of intervention, early intervention. The existing system for its evaluation are rigorous, laborious, and primarily prone to subjective disparities because different medical experts have different varying training and experiences. So in addition, most medical experts agree that there is difficulty in using microscopic images using only the naked eye. So we created an end-to-end pipeline by using AI to detect and classify this fatal disease using a multi-stage transfer learning approach, benchmark using different convolutional neural networks. Our trials show exceptional accuracy improvements against the classical or the traditional transfer learning approach. There is optimism that this research will lead to better understanding of different forms of cancers, not just leukemia, but all the cancers if done research if we have done research right on this specific field. So for our future work, so we intend to increase the efficiency of our method by including array of image enhancing techniques and benchmarking other convolutional neural networks model. So for our research, we would like to acknowledge Professor Fabio Scotti of the University of Milan for the acute lymphoblastic leukemia dataset. So thank you very much for listening.